A silicon atom has 4 valence electrons in covalent bond with other atoms, and that makes a pure silicon crystal a poor conductor. However, when doped with phosphorus, you get an extra free electron, making it a n-type semiconductor. And when doped with boron, you are left with a hole, making it a p-type semiconductor. Now, there are also gallium nitride and silicon carbide semiconductors chosen for higher voltages, faster switching, and hotter environments, each needing its own dopants, since a dopant must both fit the crystal and sit at the right energy level. When a p-type and an n-type semiconductor come together, they form a p-n junction, or in other words, a diode, that allows the current to pass from only one direction. Combinations of two such junctions form a transistor, either an NPN variant or a PNP variant. Mostly NPN variant is used, but we won't go into why. Further, there are two types of transistors, a bipolar junction transistor BJT and a field effect transistor FET, and they further have subtypes. BJTs have three terminals: emitter, base, and collector. Emitter and collector are n-type and the base is p-type. Now, immediately after manufacturing, the electrons rearrange themselves such that at the emitter base junction, the emitter end gets positively charged and the base end gets negatively charged by the free electrons that flow from the phosphorus in the n-type emitter to the holes due to the boron in the p-type base. Similar scenario happens at the base collector junction, both due to diffusion driven by random thermal motion. This creates a situation of standstill because when you connect a battery such that the positive pole sits at the collector and the negative pole sits at the emitter, the electrons rushing to the emitter can no longer pass the emitter base junction due to the repulsion from the negative charge at the base end. So essentially, the circuit is an open loop. The value of this electric potential at the emitter base junction depends upon the operating temperature and the doping density on both the sides. Usually it is 0.7 volt for silicon. So now you create an equivalent positive potential at the base terminal so that the electrons start evacuating the p-type base, neutralizing the electric field at the emitter base junction, so that the electrons can flow through the emitter to the base and then get sucked in by the external potential at the collector to finally close the circuit. The interesting part is the dynamics that play inside the p-type base. 0.7 volt doesn't free the electrons from the boron ion because breaking a bond requires much more energy. What it does is it makes the electrons hop through holes to the metal contact. Now, what is a metal contact? The copper wires forming the circuit are not directly soldered to the silicon, but there is a metal plate which too is not in direct contact with the core body of the silicon. Between them sits an extra heavily doped patch of silicon itself with the same dopants as the core body, but 100 times more concentrated, to make the Schottky barrier ultra thin for quantum tunneling to be possible in the direction of the external voltage. Look closely. In a metal p junction, metal C of electrons flow to the p-type silicon and fill its holes in the valence band, eliminating any mobile carriers due to the Pauli exclusion principle, which creates a depletion region that makes flow of current impossible unless you give electrons sufficient energy to climb up to the conduction band. Or you narrow this region to roughly 3 nanometers by doping it heavily for the wave nature of electrons to come into play. This base current in BJTs carries the signal which gets amplified at the collector. MOSFETs, on the other hand, though quite similar to the BJTs, eliminate the 0.7 volt phi and so are primarily used for on-off operations. MOSFETs, short for metal oxide semiconductor field effect transistor, has three terminals: source, gate, and drain. Source and drain are N-type and the gate sits on top of a P-type body. The gate is basically a metal plate not in contact with the P-type body like in BJTs, but having a glass insulator in between. So there is no transfer of electrons but only an induction of charge in the P-type body that creates a bridge between the source and the drain. You can think of this system as a capacitor with the glass as a dielectric. The source and the P-type body are in short circuit with each other, and more interestingly, they are deposited as hundreds of thousands of check boxes on top of the drain wafer to have a larger perimeter for the gate to work. These hundreds of thousands of units are connected such that it works as a single source, as a single P-type body, and as a single gate. Club 6 of these MOSFETs and you get an inverter that converts DC into 3-phase AC, the one used in electric motors. The MOSFETs act as switches that alternate current to the stator through the 3 phases, with 2 phases engaged at a given time, one for the positive potential and the other for the ground potential. The idle phase works in reverse and tells the controller the exact position of the rotor to calculate the time duration for a given step in the sequence, which keeps changing with the speed of the rotor. Both the switches for a given phase cannot be turned on together because that will short the battery. But for any given step in the sequence, there is a pulse modulator that controls how much of the voltage is to be supplied at any given time. In a dynamic environment, you don't necessarily want the system to only run on its maximum setting, especially when the motor is just starting up. You can control the rotation by changing the battery's supply voltage, but it is not a practical method. So what you do smartly is turn the high switch and the low switch on and off rapidly as per your desired voltage. This is called PWM, short for pulse width modulation. But you can't risk having both the switches of a given phase on at the same time. So you add a small delay, or as called the dead time, at each modulation where both the switches are off. Further, even when a MOSFET is off, it can still conduct through its PN junction at the drain with a 0.7 volt barrier we discussed earlier, which actually is an advantage because the circuit can now offer a safe path to the induced current from the motor and the leftover current of the just dropped phase back to the battery. This PN junction here is also called the body diode. In case of the idle phase, the controller ignores the current and only after its dissipation captures the induced voltage to capture the rotor's exact position. But switching a MOSFET on and off also requires a switch, which further requires a switch, and so on. To achieve this, you have gate drivers before the power MOSFET, and before them you have microscopic transistors, and even before them ultimately we have a quartz crystal that starts vibrating when powered on. This chain of transistors is what makes up the controller, but more on this later. Finally, we are left with firmware that orchestrates all of this. Firmware is a set of instructions that live in the flash cells of the controller, basically parked charges inside MOSFETs, with a small change that the glass dielectric at the gate now contains a conductive island inside which the electrons from the P-type body beneath can tunnel and stay for decades. But that cannot leak through the gate metal due to the thick upper glass in between. These flash charges partially cancel out the field of the gate, and when measured against a test voltage, tells whether an island is charged or empty, and thus giving us ones and zeros. We'll dive in more depth of this hardware some other time. So that's all that goes to run a BLDC motor. See you next week.